Hi everyone, I'm Kewen Wu from UC Berkeley. I'm very happy to present our recent work, Fourier Growth of Parity Design Trees. This is a joint work with Uma Girish from Princeton and Avi Chaitel from UC Berkeley. Let's first see what is design tree and what is parity design tree. For our purpose, we will have input x from +1 -1 hypercube and with output value in 0 or 1. On the left-hand side is one example for design tree. Each time you can query the value of one coordinate of x and branch to left or right depends on whether it's -1 or +1. And when you reach a leaf, you output the 0 or 1 value on the leaf. And then on the right-hand side is a example of parity design tree, where each time you can query a product of coordinates of x. For example, the root queries x1 times x2, and depends on whether it's -1 or +1, you goes left or right. And similarly, when you reach a leaf, you output the value of the leaf. We will allow some dummy queries. For example, this x4, no matter what its value is, we will output 1. And here are some Fourier basics. We will consider Boolean functions that the input domain is +1 -1 hypercube and output value is 0 or 1. And the Fourier coefficients are f hat s defined for each possible subset s. That is the expectation over uniform random input x, the product of x times xs, where xs is just the product of xi for all I in S. Given Fourier coefficients, we have a unique Fourier representation for every Boolean function. We can represent it by the summation of all possible s, the Fourier coefficients times the Fourier character xs. And then here is our Fourier growth. The definition is level k L1 sum, L1 kf, which is defined by this equation. The sum of all possible s of size k, the absolute value of f hat s. This quantity is useful for building pseudo-random generators for functions with small Fourier growth, and also useful for learning theory because small L1 norm implies sparse approximators in Fourier base, thus implying some efficient learning algorithm. Here are some known bounds. We remark that if we get the Fourier growth L1k is roughly at most t to the k for some parameter t, then it will have pseudo-random generators with poly t seed lengths. And such Fourier growth bounds have been verified for various computation models. For example, for small width DNFs and CNFs, and for AC0 circuit of small size and low depths, and for low sensitivity Boolean functions, and for small width read-wise branching program, for small depths randomized design trees, and for low degree F2 polynomials. In our work, we extend the Fourier growth for low depth noisy and parity design trees, and here are our bounds. And you can compare it with the previous bound of design tree, and the dependency on D is the same, D to the k over 2. This indeed suffices for applications, because for the applications, we only care about small k and when D is way larger than log n. And note that this dependence on D is optimal. That is, you cannot beat D to the k over 2. Let me mention our first application. It comes from quantum and parity query complexity. K-fold correlation is a partial Boolean function over n input bits. For our purpose, we can treat it as a black box. It is known that the quantum query complexity of this K-fold correlation is k over 2. And by our recent work, they show that the randomized query complexity of the K-fold correlation is at least n to the 1 minus 1 over k. And this is the optimal separation between quantum query complexity and the randomized query complexity. And to prove the randomized query complexity lower bound, they use the Fourier growth bound. So applying our Fourier growth bound, we show that the randomized parity query complexity and also the randomized noisy query complexity of the correlation is also at least n to the 1 minus 1 over k. The second application comes from expanded random walk. This is a recent work by Kewen, Parity, and Tashma. So we will look at functions f over plus 1 minus 1 hyper q, which satisfy the Fourier growth bound with parameter t. For example, you can apply our Fourier growth bound for parity disentries and noisy disentries here. Let G be an expander graph on n vertices such that the second largest eigenvalue is way smaller than t to the minus 4. And we will label the vertices to make sure we have half vertices with label plus 1 and half minus 1. And we consider two random distribution. The first x1 is a uniform random string in the hypercube, and second, x2 is the label sequence of an n-1 step random walk on G. And their result shows that the expectation of f under x1 and x2 are similar. The third application comes from XOR lifting in communication protocols. Assume the function f is computable by a deterministic communication protocol of cost c. This means Alice will get an n-bit string x and Bob gets an n-bit string y, and their goal is to obtain fxy after c bits of communication. In a recent work by Uma Girish, Ran Ras, and Avish et al., they define a Boolean function h by hz equals the expectation over uniform x, fx, and x times z entry-wisely. And then they propose a conjecture. The second level Fourier sum of h is at most c times polylog n. They show that the second level Fourier sum is bounded by c squared. And they also show if the conjecture is true, then the randomized communication complexity for twofold correlation composed with XOR is at least square root n. And our result shows that the conjecture is true if the protocol follows a parity disentry strategy. In the rest of the slides, I will give a proof overview. Recall our definition of level K Fourier sum, and here is our general framework. We will have a random walk perspective, which is a random top-down walk in the disentry. To illustrate this idea, I will show how to prove the level 1 bound for depth d disentries. We will show that the bound is square root d in expectation, and we will prove a concentration bound. The second idea is to use adaptive Azuma's inequality. To introduce this, I will show how to prove level 1 bound for parity disentries. The final step is a reduction for high levels to low levels. To illustrate that, I will show how to prove the second level Fourier sum for parity disentries, and it will be a reduction to the first level bound. Now, here is the proof overview for first level disentries. On the left-hand side is a disentry. Let L be a random root to leaf path, where each Li is 0 or plus 1 minus 1, and Li equals plus 1 or minus 1 if and only if xi is queried in the path and is fixed to this value, Li. For example, for the path right, and left, we will set x1 to be plus 1, x3 to be plus 1, and x4 to be minus 1. So L1 equals L3 equals plus 1, and L4 equals minus 1. Then f hat I equals the expectation over uniform x, fx times xi. And we first take the expectation over the random walk, and then take the expectation of x, conditioning on the walk. We will get f hat I equals the expectation over L, that the product of fl times Li. By negating xi in the Boolean function, we may assume the first level Fourier coefficients are all non-negative. And also, by querying dummy variables, we may assume the tree is full. And here is a dummy query. Then the first level sum equals the sum of absolute value, which we can remove the absolute value, and write it as the expectation over random paths FL times the sum of Li, which by triangle inequality, and FL is at most 1, that we get the first level bound is bounded by the expectation over L, the absolute value of the sum of Li. Now notice that the absolute value of the sum of Li depends only on the number of +1 minus 1s on the path. It is irrelevant with the query you made. So this equals the final state of a simple D-step one-dimensional random walk. And from classical results, we know that this is roughly square root D in expectation. This bound is also obtained by Ryan O'Donnell and Rocco Sabadio in 2007. For our purpose, we will get a concentration bound, that is, with probability at least 1 minus epsilon. The absolute value of the sum is at most square root D times log 1 over epsilon. To show the concentration results, let's record the standard Azuma's inequality for martingale. So here is our martingale. We start from x0 being 0, and xi equals xi minus 1 plus delta I times Ri, where delta I times Ri is a smooth on step I. Here delta I is a magnitude, which is a fixed value given previous random choices. And each R are independent random variables, that is mean 0 and also with bounded magnitude. Then the standard Azuma inequality says if the absolute value of delta I is at most Ci almost surely for each step I, then the probability that the absolute value of the final state xn being larger than t times square root the sum of Ci squared is at most e to the minus t squared. And for our decision tree model, each magnitude is 1 because you go left or right by querying one variable, and each R is an unbiased coin in +1 minus 1. So we get the absolute value of xd being larger than t times square root d is at most e to the minus t squared. By putting t to be square root log 1 over epsilon, we get the claimed concentration bound. Now let's move to parity decision tree. So on the left-hand side is a parity decision tree. Similarly, we let L to be a random root to leaf path, and each Li being +1 or -1 if and only if xi is fixed to this value along the path. And similarly, we can express f hat I as the expectation over random paths, that fl times li, and also by negating the coordinates, we assume f hat I is at least 0 for all I, and by querying dummy variables, we assume the tree is full. And then we express the first level sum by the expectation over random paths, that fl times the sum of li, which is at most the expectation over l, the absolute value of sum of li. And previously, for the decision tree part, we note that the absolute value of the sum of li depends only on the number of +1 and -1s on the path. But is it true here? So here are two paths. For example, the left-right path will fix x2 to be -1 and x5 to be +1. But since we know that x1 times x2 times x5 equals -1, so it also fixes x1 to be +1. And also for the path right, left, right, although we queried the product of x1, x2, and x5, the product of x3, x4, we can only determine x5. So we need to reweight the parity decision tree to reflect the growth of the sum of li. Here is our relabeling process. We will relabel each of the parity decision tree by the sum of newly fixed variables. For example, when we query at the root the product of x1, x2, and x5, although we know whether it's +1 or -1, we do not fix any individual xi. And then if it goes left, it will query x2, and thus fixing x2 to be +1 or -1. And then it goes left, for example, and query x5. Then not only it fixes x5, but also fix x1 because we know the parity of x1, x2, x5, and know the value of x2 and x5. Therefore, the sum of Li equals the sum of edge weights. And then we can upper bound the first level sum by the expectation over L, the up to value of the sum of edge weights. The good thing of this expression is that it's still a one-dimensional random walk because on each query, it either goes right or left with half probability, and their edge weights are opposite. However, each step size now is not fixed, but adaptively determined based on the path. To apply some kind of Azuma's inequality, we need to make sure the step size are smooth. Here, we are inspired by the work of Blas, Tan, and Wan in 2015. For example, if we first query x1, y1, and then query x1, y2, and then x1, y3, and then x1, y4, and then x1, then we will fix 5 variables, x1, y1, y2, y3, y4, in the end. However, if we query x1 right after x1, y1, and then make the query of x1, y2, x1, y3, and x1, y4, we will fix the variables gradually. And also for our purpose, the standard Azuma's inequality doesn't suffice, so we need some kind of adaptive version of Azuma's inequality to obtain concentration bonds. Now I explain the adaptive version of Azuma's inequality developed for our purpose. The setting is the same as before. We start from 0 and make a mean zero random walk each time. And here, delta I is still the magnitude, which is a fixed value given previous random choices, and each Ri are independent random variables that is mean zero and with bounded magnitude. So for adaptive Azuma's inequality, it says if the sum of delta I square is at most U or most surely, then we get the similar looking concentration bound. That is, the probability that the absolute value of the final state being larger than t times square root u is at most e to the minus t square. Here, you can compare it with the standard Azuma's inequality, where u is set to be the sum of ci square, where each ci is the maximum possible step size. And actually, for our proof, we will use adaptive Azuma's inequality with arrow. That is, we assume this condition is violated with probability at most epsilon. Then we will get an additional epsilon factor here for the concentration bound. Here is an example that we will use to compare the three Azuma's inequality that we mentioned. Note that C1 here equals 0, and C2 here equals 1, and C3 here equals 2. So from standard Azuma's inequality, we will have the sum of ci square equals 5. However, for the adaptive version of Azuma's inequality, we look at each path individually and compute the sum of step size square. That is at most 4 here. And if we allow making error, then we can discard the move here. And then u equals 2 with probability 3/4. Finally, let me sketch the proof for the second level sum for parity entries. Still, let L be a random root to leaf path, and Li equals +1 or -1 if and only if xi is fixed to this value along the path. Then we can express f hat ij equals expectation of x, fx times xi xj, which equals the expectation over the path L, fl times the expectation of x, conditioning on L, the product of xi xj. And can we hope for replacing the inner expectation by Li Lj here? Here is an example. Assume we only query the product of x1 and x2. Then individually, we do not fix x1 nor x2. However, we fix their product. So this red equation does not hold anymore. But for our purpose, we will do a cleanup. That is, whenever we have a parity at hand, we will query one of them to make sure the equality holds. For example, after we query the product of x1 and x2, we will query x1 immediately. so that the expectation of the product of xi xj equals li times lj. And using this, we can break the correlation. The second issue is from the sign. Because we are now at the second level, then we cannot assume they are all non-negative. So we take out the sign by setting aij to be the sign of f hat ij. Then we can express the second level sum as the sum of aij times f hat ij. And by the similar analysis, we can upper bound it by the expectation over L, the absolute value of the sum of aij times li times lj. To do so, we need to assume we did the cleanup to break the correlation. The growth of the sum of aij times li lj at step t can be written as a level 1 bound of a depth t parity disentry. Intuitively, this is because the derivative of a quadratic is a linear function, and the second level Fourier sum is a quadratic. And then we promote the second level bound to the third level and up to level k. In summary, we prove Fourier growth of randomized parity disentries and noisy disentries. And our techniques is by first viewing the Fourier sum as a random top-down walk of the tree, and then use an adaptive version of Azuma's inequality, and then we induction on the levels of Fourier bounds. And also we have applications in the separations between quantum and parity query complexities in expander random walks, and also in XOR lifting problems in communication complexity. Here we mention two open problems. The first is what we mentioned in the application, the second level Fourier bounds for XOR lifting in communication complexity. We only verified it if the XOR lifting protocol is parity disentry strategy. And the second open problem is the tight bound for the Fourier growth. There is a gap of roughly k log n to the k between upper bounds and lower bounds. It would be nice to close the gap. Thanks for listening.